A black hole's edge is a point where 100% of known physics breaks down completely. A 2020 study in Physical Review Letters confirmed that no known force can survive that boundary. But your body right now is safe only because you are billions of miles from the nearest one. In November 1915, Albert Einstein stood before the Prussian Academy and unveiled his final equations for general relativity. Yet a dying man had already mailed him the mathematical key to that edge, a letter from hell itself. Gravity, he proposed, was not a force pulling across empty space. Gravity was the curvature of space-time itself, a warping of the cosmic fabric caused by mass and energy. The equations were so fiendishly complex that even Einstein, the greatest mind of his generation, could only find approximate solutions. The exact behavior of space-time around a single, isolated mass remained a ghost in the machine. The problem was considered nearly unsolvable. 2 months later, in January 1916, a 42-year-old artillery lieutenant named Karl Schwarzschild sat in a dugout on the Eastern Front. The ground was frozen. The war had already consumed millions of lives. Schwarzschild was one of Germany's most respected astronomers, director of the Astrophysical Observatory in Potsdam. But now he calculated shell trajectories instead of stellar orbits. Somehow, between artillery barrages, he obtained Einstein's papers, and he began to work. Schwarzschild made a crucial simplification. He assumed a static, spherical mass in a perfect vacuum, no rotation, no charge, no external interference, just a lone star sitting in empty space. With that assumption, he cracked the equations open. He found an exact solution, and then he wrote to Einstein from the front, enclosing his results in a letter that would survive military censorship and change physics forever. Einstein received the letter and was stunned. He replied with admiration, calling Schwarzschild's work a wonderful result. But he also noted something deeply troubling. The mathematics predicted a point, a specific radius, where the equations exploded to infinity. At that boundary, the curvature of space-time became so extreme that not even light could escape. Einstein called it the Schwarzschild singularity. He believed it was a mathematical artifact, a flaw in the theory that nature would surely prevent. But Schwarzschild's solution said otherwise. If enough mass was compressed within that critical radius, for the Sun, about 3 kilometers, space-time would fold in on itself completely. A region would form where gravity becomes absolute. No signal, no particle, no information could ever leave. The edge of doom had a name, the Schwarzschild radius. What started as a theoretical curiosity was about to rewrite the laws of physics. But the most shocking part of this story hasn't even begun. Karl Schwarzschild was born in 1873 in Frankfurt, Germany, into a family deeply embedded in the intellectual fabric of the nation. By the age of 16, while most boys his age were memorizing Latin declensions, he had already published a paper on celestial mechanics, a rigorous analysis of orbital perturbations that caught the attention of professional astronomers. This was not a prodigy dabbling in amateur enthusiasm. This was a mind operating at a professional level before he could vote. By 23, he held a professorship. By his early 30s, he had been appointed director of the Astrophysical Observatory in Potsdam, arguably the most prestigious astronomical post in Germany. He was that rare figure in science, a master of both pure theory and hands-on observation. He could derive equations that made colleagues blink in disbelief, then walk outside and calibrate a telescope himself. He understood the stars mathematically and physically. When World War I erupted in August 1914, Schwarzschild was 41 years old. He was beyond conscription age. He held a position of immense institutional value. He could have stayed in Berlin, continued his research, and waited out the war in relative safety. He did not. He volunteered for military service. This decision remains one of the most haunting in the history of physics. He was assigned to the Eastern Front as an artillery lieutenant, tasked with calculating ballistic trajectories for German guns. The irony is almost unbearable. The man who would map the geometry of space-time was now mapping the arc of high-explosive shells across the frozen fields of Russia. The Eastern Front in 1915 was not a place for intellectual work. It was a landscape of mud, snow, cholera, and constant artillery exchange. Temperatures dropped so low that ink froze in its bottle. Soldiers died from disease faster than from bullets. Yet Schwarzschild, between ranging calculations and military drills, managed to obtain copies of Einstein's newly published papers on general relativity. He read them in a dugout by candlelight. And then, with the patience of a man who had spent years studying the subtle dance of binary star systems, he began to attack the equations. The paper he produced, on the gravitational field of a mass point according to Einstein's theory, was published in the Proceedings of the Prussian Academy of Sciences in January 1916. It arrived in Berlin from the front lines, submitted by a man who was simultaneously calculating the death of soldiers and the death of stars. The paper contained two predictions that would reshape physics forever. The first was the Schwarzschild radius, the critical boundary where gravity becomes so intense that space-time essentially tears away from the rest of the universe. The second was the Singularity, a point of infinite density at the very center of this collapsed object, where the known laws of physics break down completely. Einstein received the paper and was deeply unsettled. He referred to the Singularity as a blemish on his theory, a mathematical flaw he believed nature would never permit. He argued that real matter could never compress to such an extreme state, but Schwarzschild's equations were clear. If enough mass is squeezed inside that critical radius for an object the mass of our Sun, about 3 kilometers, the collapse becomes inevitable. Gravity wins. Space-time closes its own door. Schwarzschild never saw the full impact of his work. In the spring of 1916, while still serving on the front, he contracted pemphigus, a painful autoimmune disease that caused his skin to blister and peel. He was evacuated back to Germany, but the damage was done. On May 11, 1916, Karl Schwarzschild died. He was 43 years old. He left behind a wife, 2 children, and a mathematical ghost that would haunt physicists for a century. The Schwarzschild radius is not a surface you can touch. It is not a wall of fire or a physical shell. It is a mathematical boundary in space-time itself, a point of no return defined purely by geometry. For any non-rotating mass, this critical radius is calculated by a remarkably simple equation: 2 times the gravitational constant times the mass divided by the speed of light squared. Plug in the numbers, and the universe reveals its limit. For an object with the mass of our Sun, that radius is approximately 3 kilometers, about 2 miles. Compress the Sun to the size of a small town, and space-time caves in. For Earth, the Schwarzschild radius would be just 9 millimeters. The entire planet, all 5.97 times 10 to the 24th kilograms of rock, iron, and ocean, would need to be crushed down to the size of a marble. That is the threshold. Cross it, and gravity becomes absolute. Let us make this concrete with an analogy Susskind himself might use. Imagine standing on the surface of Earth and throwing a baseball straight up. To escape Earth's gravitational pull entirely, you need to launch that ball at 11.2 kilometers per second, the escape velocity. Throw it slower, and it arcs back down. Now imagine standing on the surface of a neutron star, a city-sized sphere of nuclear matter so dense that a teaspoon weighs 1 billion tons. To escape that gravity, you would need to throw the baseball at half the speed of light. At the Schwarzschild radius, the escape velocity reaches 300,000 kilometers per second, the speed of light itself. And since nothing with mass can travel that fast, and light itself cannot climb out of a gravitational well this deep, the baseball never leaves. Nothing leaves. The boundary is absolute. Inside that radius, the geometry of space-time undergoes a fundamental inversion. In normal space, you can move in any direction: forward, backward, left, right, up, down. You have choices. Inside the Schwarzschild radius, all possible paths lead inward. Space itself becomes a one-way street. The future points only toward the center. You could fire your rocket engines with maximum thrust directly away from the singularity, and it would not matter. You would still move inward, not because a force is pulling you, but because space-time has been so severely warped that outward no longer exists as a direction. This is not a matter of insufficient power. It is a matter of geometry. The event horizon is the place where the map of space-time tears in half. At the very center of this collapsed region lies the singularity. This is where the mathematics of general relativity reaches its breaking point. Density becomes infinite. Space-time curvature becomes infinite. The equations produce a division by zero, a literal infinity that physicists call a naked breakdown of the theory. The known laws of physics cease to apply. Time, as we understand it, stops having meaning. The singularity is not a point in space the way a marble is a point in space. It is a moment in time, the inevitable endpoint for anything that crosses the horizon. Every path leads there. Every particle that falls in arrives at the singularity in finite proper time. There is no way to stop. There is no way to turn around. The singularity is the future. Einstein found this deeply disturbing. He spent years searching for some mechanism, some yet undiscovered physical process, that would halt the collapse before the singularity formed. He published papers attempting to prove that matter could never compress to infinite density. He was wrong. Nature does not care about elegance. Nature cares about mathematics, and Schwarzschild's mathematics was merciless. The tragedy is that Schwarzschild himself never knew the full weight of what he had discovered. He died in May 1916, just months after his paper was published, before the debate even began. He never saw the singularity become the central obsession of theoretical physics. He never saw his name attached to the radius that defines every black hole in the universe. He died in a hospital in Potsdam, his skin blistering from pemphigus, his body ravaged by the same war that had given him the time and solitude to solve the unsolvable. For the next 23 years, the Schwarzschild solution gathered dust. Physicists read it, nodded politely, and filed it away as a mathematical curiosity, an elegant but physically meaningless artifact of the equations. The consensus was simple. Real stars would never collapse to such an extreme state. Internal pressure, nuclear fusion, some unknown quantum effect. Something would intervene before space-time tore itself apart. Einstein himself argued this repeatedly. The Schwarzschild singularity was a blemish, not a prophecy. Then came 1939. Robert Oppenheimer, then a 35-year-old physicist at the University of California, Berkeley, was not convinced by the consensus. He had been studying the final stages of stellar evolution. What happens when a massive star exhausts its nuclear fuel and can no longer fight gravity? Working with his graduate student Hartland Snyder, Oppenheimer published a paper titled On Continued Gravitational Contraction. The title was deliberately understated. The content was devastating. They showed that a star with more than about 3 times the mass of the Sun would undergo an unstoppable collapse. No force in the universe, not neutron degeneracy pressure, not nuclear repulsion, not quantum effects, could halt it. The star would shrink past its Schwarzschild radius in finite time, and once it crossed that boundary, the singularity at the center became inevitable. Oppenheimer called it a frozen star, because, to a distant observer, time itself appeared to stop at the horizon. Oppenheimer's paper should have ignited a revolution. Instead, it was almost completely ignored. World War II erupted months after publication, and Oppenheimer himself was soon consumed by the Manhattan Project, directing the creation of the atomic bomb at Los Alamos. The frozen star, the very object Schwarzschild had predicted from a trench, was forgotten. Physics had more urgent problems: splitting the nucleus, ending a war, building a weapon that could annihilate cities. The black hole, still unnamed, waited in the dark. In 1967, at a NASA conference in New York, John Archibald Wheeler, a Princeton physicist who had studied under Niels Bohr and worked alongside Einstein, grew frustrated with the clunky terminology. He stood before the audience and proposed something simpler, something darker. Black hole. The name spread like a fire through the scientific community, and within a year, it had escaped the confines of academia entirely. It entered newspapers, radio broadcasts, and late-night conversations. Wheeler had not discovered black holes. He had given them a name that captured the human imagination, a name that made the universe feel dangerous again. But a name alone cannot confirm existence. Throughout the 1970s, physicists needed evidence. They needed to find something real in the sky that matched Schwarzschild's mathematics. The first candidate emerged in 1971 when astronomers detected a powerful X-ray source in the constellation Cygnus, designated Cygnus X1. The object was invisible in optical telescopes, but it was pulling gas from a visible blue supergiant star. As that gas spiraled inward, it heated to millions of degrees, emitting X-rays that could be detected from Earth. The mathematics of the orbit revealed the invisible object's mass, approximately 15 times the mass of the Sun, compressed into a region too small to be a neutron star. By the laws of physics, it could only be one thing. Stephen Hawking and Kip Thorne famously made a bet about whether Cygnus X1 was truly a black hole. Hawking, skeptical, conceded the bet in 1990 when observational data became undeniable. The first black hole had been found. The evidence accumulated through the 1980s and 1990s. Quasars, brilliant points of light at the centers of distant galaxies, were revealed to be supermassive black holes consuming vast amounts of gas, their accretion disks outshining entire galaxies. Astronomers mapped the orbits of stars near the center of our own Milky Way, watching them whip around an invisible object with the mass of 4 million suns. The object, designated Sagittarius A, was invisible, but its gravitational influence was unmistakable. The stars moved exactly as Newton and Einstein predicted they would if something massive and compact sat at the galactic center. Every orbit was a confirmation of Schwarzschild's solution. The Event Horizon Telescope collaboration, a global network of 8 radio observatories synchronized to function as a single Earth-sized telescope, turned its attention to the supermassive black hole at the center of the galaxy, M87, 55 million light-years away. After years of data processing, the team released an image that stopped the world. What they showed was not a photograph in the conventional sense. It was a reconstruction of radio waves, translated into visible light. But the structure was unmistakable. A dark, circular shadow, surrounded by a glowing ring of orange and yellow light. That shadow was the event horizon. That ring was the accretion disk, superheated gas swirling at near-light speeds, its photons bent by gravity into a perfect circle. The diameter of the shadow matched the Schwarzschild radius, calculated from M87's mass to within 10%. The mathematics from 1916, written in a dugout on a frozen battlefield, had been visualized across a distance of 55 million light-years. The image was not just a triumph of engineering. It was a confrontation with the absolute. Every photon in that image had been stretched and bent by space-time curvature, so extreme that the light itself had to climb out of a gravitational well deeper than any other in the known universe. The shadow at the center was not a solid object. It was the absence of light, the visual signature of a region from which no photon can escape. It was the first time humanity had seen, with its own eyes, the edge Karl Schwarzschild had calculated a century earlier. And that edge raises a question we still cannot answer. Inside the shadow, at the very center of every black hole, lies the singularity, the point where density becomes infinite, where space-time curvature becomes infinite, where the equations of general relativity divide by zero. What happens there? Does quantum gravity, the yet unknown theory that unifies general relativity with quantum mechanics, rewrite the rules? Does time itself end, as the mathematics suggests? Or is the singularity a door, a bridge to another universe, another region of space-time entirely? We do not know. The theory breaks down exactly where we need it most. Schwarzschild gave us the edge. He could not give us what lies beyond. That is the unfinished business of physics. Every black hole in the universe, from the stellar mass remnants scattered across our galaxy to the supermassive giants at the centers of galaxies, contains a singularity at its heart. Every one of them is a place where our understanding of reality collapses. The Event Horizon Telescope gave us the shadow. It did not give us the interior. That remains the last frontier, the boundary where general relativity meets its match and quantum gravity must take over. The next generation of telescopes, including the proposed Black Hole Explorer mission, aims to image black holes with even greater resolution, perhaps revealing the photon ring, the narrow orbit where light circles the black hole indefinitely. But the singularity itself may never be directly observed. It is forever hidden behind the horizon, protected by the very geometry Schwarzschild discovered. Karl Schwarzschild never knew the word black hole. He died before the term was coined, before the first candidate was detected, before the image that confirmed his mathematics. He left behind a wife, 2 children, and a solution to a problem most of his contemporaries had not even fully understood. He had been right about something so profound that it took humanity over a century to prove it. And in that proof, we confront a truth that is both humbling and exhilarating. The universe is not only stranger than we suppose, it is stranger than we can suppose.